So if you remember back to uh, properties of and states of matter, gases are easily compressed, highly compressible, because the space between the gas molecules is large compared to the total volume itself. This also explains the pressure versus volume. When you increase the pressure of the outside of the gas, eventually you're going to get to the point where they can't be compressed anymore. And that's why the graph starts to level out as you get to higher pressures. There's three main things affecting the air pressure: the amount of the gas. So as you increase the number of moles of gas, or the amount in uh, into your volume, that increases the air pressure. So think of putting air inside a tire. The volume of the container. So if you increase the volume of the container or decrease the volume of the container, it's going to increase or decrease the pressure and therefore the temperature. And then the temperature. So if you think about a tire, if we increase the size of the tire without adding any more uh, gas inside, the pressure will go down. It also highlights the difference between winter and summer air pressure. Uh, Oftentimes during the winter, the air pressure inside the tire will decrease, and you actually need to add more air inside the tire to keep it inflated. Like temperatures today, a lot colder than they normally are in the summer. So if you got your last time you put air in your tire and it was in the summer, uh, your tire pressure will be low. Now we're going to get into the gas laws. These are things that you need to know, especially how the graphs look. So this is something that should look familiar because it's your pressure versus volume. Boyles Law. Boyles Law is the only inverse relationship in the gas law. So the increased pressure, decreased volume, but it's not a perfect linear relationship or proportional. It's inversely proportional. You can tell because of the curved line. However, you don't know exactly how it inversely proportional is just by looking at it, but we do know that the pressure is proportional to 1 over volume. All right, so as our pressure increases, our volume here will decrease. So as our pressure increases here, our volume will decrease. As it decreases, our volume increases. Next one we're going to look at is Charles' Law. That's temperature and volume. I'm going to use a way to help you remember this. Steal it from Mrs. Teston. She always taught it as Charlie Sheen is on TV. So Charles' Law is temperature and volume. We know that as temperature increases, we know that it's proportional to a volume increase. All right, so that we know they're directly proportional. So it's not exactly equal, right? So if we increase 1 atmosphere, it may decrease half a liter, but it is proportional. So you should have seen that as you heated up your balloons. You got a related increase in volume. Think hot air balloons, or if you cooled it down, you should have got a proportional decrease in volume. And this should have had a linear relationship, so we're pretty close to it. So as temperature increases, the volume, oops, that is not right. So as temperature increases, the volume increases. So Charlie Sheen is on TV. And then the last law that you need to know, at least for this is especially true for like multiple choice test question, Gay-Lussac's law. Again, Mrs. Teston would say, TPing a house makes you happy and gay. So TPing, as in toilet papering someone's house, makes you happy and gay. So Gay-Lussac's law. So pressure and temperature. We also know that pressure and temperature are directly proportional. So as you increase pressure, increase the temperature, or vice versa. So if you increase the temperature, you increase the pressure. Or if you decrease the pressure, you decrease the temperature, or if you decrease the temperature, you decrease the pressure. So whichever one you do change, you're going to have a proportional change in the other variable. So what does this all mean? Well, we get something called the combined gas law. So if we want to know how much gas we have to add, we have to add moles. So we get something called the combined gas law. So if we have a change in, so if we have one gas, so one balloon, so here's our balloon with gas, it has a certain volume, has a certain temperature. So if we do any kind of change to it, and we want to find out how that changes the other factors, then we use this combined gas law. So we use, all right, so this is the pressure, volume, temperature, moles of 1. And if we change anything on here, so if we say, all right, what happens to the pressure when we change the temperature? Well, we know the pressure of 1, we know the temperature of 1. Well, if we increase the temperature, how does the pressure change? Well, it's proportional to P2 over T2. So you just use what you have changed and what you know from each of these equations. Everything else you can get rid of. We'll go through some examples later, so hopefully that makes more sense later. But this combined gas law really is the only one you need. So even though you need to know like the Boyles Law curve, you need to know Charlie Sheen is temperature and volume, you need to know that Gay-Lussac is temperature and pressure. Really, with doing calculations, you're only using the combined gas law. So, for example, a gas has an initial volume of 14.2 liters at 190 kilopascals. The pressure is dropped to 130 was the resulting volume. So if we use our, oops, let me change the pen color here. That doesn't help. All right, so let's do it here. So we have pressure, PV, T, N, 1. So we are looking at just pressure and volume. So really we don't need to know the T and the N. We're just looking at P1, V1, So we don't really care because that's held constant, so those are going to stay the same, so we can cross those out because they would be constant on both sides. The only thing that's changing is our P1, or sorry, V1 here, and P1. We have a P2, so we just want to look at what the volume is. So we can put those values in, so this would be volume 1, pressure 1, this would be pressure 2, and we're just solving for V2. So we can put 14.2 times 190, and then we know P2, so we're going to divide that by 130 because we're doing cross multiplication or cross division here, equals V2. Then you should be able to solve for that. Alright, so our next example is another gas has a temperature of 16.9, so this is a T1 and a volume of 10 liters, so that's V1 at 1.09 atmospheres, so that's P1. So if the pressure is raised, so this is a P2, and the volume is dropped, so this is our V2, what's our resulting temperature? So what do we have? So we have P1, V1, T1, P2, V2, with the moles being constant. So we can, so in our original equation we can leave, so we have P1, V1 over T1, N1 equals P2, V2, T2, N2. Again, since the moles cancel when you cross multiply, if they're the same, they cancel out. Then we just substitute and then cross multiply. So we're going to be solving for T2 here. All right, so what we're going to do is then substitute all these things. So we have 16.9 be our T1, so that'd be 16.9 on the bottom. Volume 10 times 1.09 so, and then we have equal to P2, so that'd be 1.5, and notice I'm leaving out the units, which is normally bad, but since I'm drawing with this goofy pen and a mouse, I'm kind of leaving them off. And then 5 liters is your volume 2, and then your T2 is what you're solving for. So cross multiplication and solving for T2, you should be able to get that answer. Awesome. So let's talk about ideal gases versus real gases and the ideal gas law. So this can be used to calculate additional information about gas that is not changing. So notice that we have not changing. So whereas the combined gas law we use for one gas that is changing, the ideal gas law can be used to figure out the state of one gas. If we knew the pressure, volume, and temperature of a gas, we could find out how many moles it has. If we knew everything except one variable, we can find out the last one. In this, we use the gas constant, which is our proportionality constant or slope with those other relationships, which is 8.31 liters kilopascals mole Kelvin. So if you use kilopascals, it's 8.31. If you use atmospheres, then you have to use 0.0821 because of the difference in units. Remember, 1 atmosphere is equal to 101 point. Always forget 101.3 kilopascals. So there's a unit difference. So we essentially multiply it times 100, and you get that difference. So your units must match the constant. So that's one of the key ideas here. So if we have one gas that's not changing, we use the ideal gas law. Alright, so what is the ideal versus real? The ideal gases are assumed to be exactly follow the kinetic theories and occupy no space, have no interactions, constantly moving. But real gases don't exactly follow this. They tend to follow it fairly close, except for a couple of situations. And those are at very low temperatures. So the closer you get to 0 degrees Kelvin, the less likely they are to follow ideal gas. So you can think about an example of carbon dioxide. So if you get really low temperature, even well before 0 Kelvin, it starts to turn into a solid, and therefore is not a gas. Liquid nitrogen, once it liquefies, it's no longer a gas, so can't be an ideal gas at all. And then high pressure, so you can think of high pressure gases like propane, methane. As soon as they're under high pressure, again, they turn into liquids and aren't gases. All right, the last thing that we're going to go through is Dalton's Law. So this is gas mixtures and movements. Dalton's Law, total pressure in a system is the sum of the partial pressures. So if we know, and we'll go through this in class a little bit more, but so P total. So if we're thinking about air pressure, we know that air pressure is a mixture of the pressure of all the gases in it. So if you think about what most of air is, that would be the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of carbon dioxide. Those are, of course, the 3 main ones, but there's a lot of other ones in air, including H2O and a bunch of other gases as well. So all those gas pressures combined will equal the total air pressure. The next thing is Graham's Law. This is about diffusion and infusion, so going from high concentration to low concentration. In a fusion, molecules of gas escaping from a hole in their container. So gas escaping or diffusion is relative to the mass of the molecule. So the lower the mass, the higher the rate of speed. So larger molecules tend to diffuse or effuse slower than smaller ones. Alright, that's all I have for you guys today. I do have some practice problems that I want you guys to work through now after you've completed the notes. And then remember, your gas law lab summary is due to me tomorrow. I'll see you guys Thursday, and hope you had a great break. Let me know if you guys have any